Energy and momentum, when the objects in question are moving very fast, that is, they have relativistic motions. So in special relativity, energy and momentum, we need new definitions. Basically, the classical definitions, they're not good enough when speeds are relativistic. So the classical definitions are simply that the momentum vector is the mass of the object times the velocity vector, and the kinetic energy, which is a scalar quantity, right? It's not a vector, is 1/2 mv squared. And then when there is no potential energy to talk about, the total energy is just simply equal to the kinetic energy, the motion of mass energy, right? And when I am talking about relativity right now, we're not going to have a potential energy. Yeah, so the idea is why are these not good enough? And the answer is they are not conserved for all inertial observers. In a really early video, I showed you actually that classical relativistic velocity transforms actually conserve momentum, and they also do the right thing with the conservation of energy. But the problem is because we are dealing with relativistic speeds, like relativistic motions, we have to use the relative, like special relativity velocity transforms. And when we use special relativity velocity transforms, these classical definitions, they don't behave in a conservation way. So what we need to do is we need to create new definitions for relativistic energy and relativistic momentum that actually are conserved. So I'm going to write these relativistic definitions are conserved for all inertial reference frames or inertial observers. So the new definitions, they look really similar to the old ones. For momentum, the new definition looks the following way. Still looks like m times v, but there is a division by the square root of 1 minus the magnitude of the speed squared divided by c squared. So that's the relativistic definition of momentum. And then the relativistic definition of kinetic energy gets updated as well, except for it looks a little bit crazy. So there is an mc squared divided by square root of 1 minus v squared over c squared. So that's the velocity of the object squared. That's the speed of light squared. That's the mass of the object. And then, yeah, the speed of light's down here as well. So that's the kinetic, well, actually, I'm not finished writing the kinetic energy. The kinetic energy has a subtraction of mc squared. So this is very strange. The idea is, so also when there is no potential energy, the total energy is going to be the kinetic energy, but plus something called E sub 0, where E sub 0 is called the rest energy. It's equal to mc squared. So this is called the rest energy, and this is one of the most famous equations in all of physics. E equals mc squared is right here. It's associated with rest energy. This capital E, this is the total energy in the absence of any potential energy. It looks really similar, except for the relativistic version of the total energy is kinetic plus rest. So this is kinetic plus rest energy. So the total energy has a rest energy component, which classically it doesn't have that, right? So there is no rest energy to worry about. Yeah, so an update in relativity, when you think about energy, actually, one of the forms of energy that comes along with kinetic is rest energy. Isn't that strange? That's pretty neat. The total energy, if it's the kinetic plus this mc squared, and the kinetic is this weird expression minus this mc squared, the total energy is simply just the first term in the definition of the kinetic energy. It's mc squared over the square root of 1 minus the speed squared divided by speed of light squared. So these are the appropriate definitions of kinetic energy, the total energy, but what comes along for the ride is this new form of energy. And again, these relativistic definitions, the reason that they are taken as the things that are going to work is because with these definitions, there is a conservation rule. That's the point. There is a conservation rule. So there's only a conservation rule in relativistic definitions of energy and momentum if there is this idea of the rest energy. Let me show you something interesting. If you do some algebra, you can get this statement about the energy of a particle. So you can get this thing that looks like this. The total energy squared is equal to the momentum times the speed of light squared plus the rest energy squared. So this statement here, it comes from, you do some algebra, comes from the definitions for the various relativistic versions of momentum and energy. So the momentum is m times v, so that's the velocity vector, the momentum vector, divided by square root 1 minus speed squared divided by speed of light squared. And then the kinetic energy plus the rest energy is, this is what is the total energy of a particle, and it's equal to mc squared divided by square root 1 minus v squared over c squared. And so I bet you can sort of see how you can take these things, right, with some algebra, you can get this. So this is just another way to look at the same, or it's actually, you know what it is? It's a relationship between momentum and energy. Here's the energy, here's the momentum. These are the separate descriptions in terms of sort of more basic issues like mass and velocity and the speed of light. And here is an algebraic relationship between the two separate quantities. So what you can do with this, though, this is pretty cool. So a cool mnemonic device. So a cool mnemonic device is based on this relationship. it's when you realize that this looks kind of like Pythagorean theorem. So this is, of course, not the Pythagorean theorem. It just sort of looks like it. So, so it looks like this. And so I'm going to take this thing and realize it or think about it in terms of a right triangle. Because remember, the Pythagorean theorem is about right triangles. So it looks like PC squared plus MC squared squared is equal to the hypotenuse squared. So the hypotenuse is the total energy. It doesn't really matter which side is which, but I'll give the small side the momentum piece, and then I'll give the slightly longer looking side the rest energy piece. Right? And so, okay, so you can look at this triangle and sort of see this relationship. There's a PC component to the total energy, and there's an MC squared component to the total energy. All right, so this little mnemonic device actually becomes a little bit cooler if you start to wonder about an angle. So I'm going to call this angle theta, and I'm going to take the sine of theta. So the sine of theta is PC divided by E, the total energy. And so PC, you can get PC from here, right? So you just multiply C on both sides and take the magnitude. It'll be MCV over the square root of the stuff. And then you divide by E, and E is here. And if you just do the algebra, you notice that actually the top and the bottom have the same factor of 1 divided by the square root of 1 minus V squared over C squared. So if you take these things and do some algebra, you can get that what this is equal to is V over C. It's the ratio of the speed of the particle in question divided by the speed of light. Yeah, so this is pretty cool. It's just an interesting thing to have. So the sine of the angle is this ratio. So I'm going to tell you why this relationship is useful. And I'm going to do that by way of thinking about light. So let's use this stuff to think about a photon. So a photon, right, is a little particle of light. So photons are particles of light. Yeah, so this little particle of light travels at speed c, right? Light particles travel at the speed of light. So, but it also has the quality of having no rest mass, right? So these are sort of interesting. So if you go in, so let's use this stuff to think about the photon. So one of the things we can think about is rest energy. And so, you know, it's mc squared. And the idea is both m and c are sort of invariant quantities. And if, so the idea is like, if there is a an inertial observer or observer frame that sees that the mass is equal to 0, then because we're talking about mass and it's invariant, every observer sees it to be 0. So, okay, so no big deal. I mean, I guess this is the case for photons. There's no rest energy associated with a photon because there is no mass, right? No inertia associated with a photon. Let's check something else. So what about the momentum of a photon? So here's the momentum definition. So the momentum is equal to, so m times v divided by square root 1 minus v squared over c squared. And so let's just, why don't we study actually the magnitude of the momentum of a photon? So the bottom is never negative, the mass is never negative, so this must be just mass times that. And a photon, right, it has 0 mass. The speed is the finite speed c, right? But then we're dividing by the square root of 1 minus 1, right? So we're getting 0 over 0. It is undefined. So I'll put a undefined, right? What do we do with this? But before we move on, let's check something else we can also look at. Let's look at the kinetic energy. So the kinetic energy of a photon, so T is equal to, so there's this mc squared divided by square root 1 minus v squared over c squared, but then you subtract off the rest energy. So the rest energy is 0, the mass is 0, so there's a 0, and then, but I'm dividing by, once again, 0, right? So this right here is concerning, isn't it? So it's undefined as well. So what's really cool is actually our mnemonic device saves us. So it comes to the rescue. And the way it does this is we just look here. It looks like, so our mnemonic device has the sine of theta, right, equal to v over c. So at this point we're looking at sine of theta equal to v over c is equal to c over c for a photon, right? We're talking about photons. Photons travel at the speed of light. So the value of the speed of our photon is the speed of light, and this is 1. And this implies that the angle theta is 90 degrees, right? So 90 degrees, what does that look like? What that looks like is we are getting into a position where if this is the angle theta and it also needs to be 90, we have PC and E, and this is 0. I wonder if you can see this in our mnemonic device. And what this is implying for us is that the energy of a photon, so we're talking about a photon, it's equal to P times C. Right? So this is what we can get from our mnemonic device. The mnemonic device is actually quite quick. All you'd say is, well, photons have no rest energy, so this term is 0, and what's left over is the energy squared of a photon is the momentum of a photon times the speed of light, all squared, right? Which is what this says right here in terms of magnitudes. So this is how you think about photons. It's interesting, I think, to point out. So let me make a bit of a note. So some notes. I'm going to put a few notes on this page. So the first note has to do with what we just discovered. Right? For photon, the energy of the photon is equal to P times C. Right? For photons, if you go in and look at the definition of momentum in terms of a material object, right, an object with matter, made out of matter, I get this undefined thing. So what's interesting is you can kind of E and P for photon are well defined. At least the relationship between the energy and the momentum of a photon. Yeah, so maybe, yeah, I'm going to leave it like this. And the relationship between the energy and momentum is just this relationship here. Okay, so, and yeah, like, let me just add this. So we are talking about the magnitude of a vector momentum for a photon, right? Where the direction is just the direction of travel of the photon. Okay, so, yeah, I've got this note for the photon. Another note. So here is one note, another note. Okay, so it turns out, like, if you think about it, so think about it a bit. For a massless particle to have any momentum or energy, it must move at speed of light. Right? So up here, if I have a massless particle that travels at less than the speed of light, then I'm just going to always calculate for my massless particle 0 momentum and 0 energy. Right? That's what I'm going to calculate. So, so if I have an object that moves at slower than the speed of light and has no mass, then the truth is it cannot participate in a physical way in anything, because it won't deliver momentum, it won't bring momentum in or take momentum out, and it won't adjust energies. It's sort of the most uninteresting thing you can imagine. There were, yeah, so I'll leave it like that. Let's have a massless particle, if we're talking about massless particles, of which the photon is an example. It has to travel at the speed of light to have momentum and energy. Okay, so those are a couple of notes. Here's another note, and this note's pretty cool. So these new definitions of momentum and energy, as well as kinetic energy and rest energy, right? So these new definitions of momentum and energy satisfy conservation of momentum and energy for all inertial observers. And the connection, right? So the connection between observers is given by Lorentz velocity transforms, right? So yeah, so if you look at these definitions of momentum and kinetic energy, they depend on the velocity vector, and they depend on the magnitude of the velocity. So the idea is you might have an observer, right? O sees, say, V1, V2, V3, etc. O prime is going to see other data. So O prime is going to see V1 prime, V2 prime, and V3 prime, and the connection between these two sets of velocity data is Lorentz transformations, right? So in O, you'll see conservation. And then in order to see conservation of momentum and energy in O prime, you have to convert all the velocities over. But what's interesting here is c, the speed of light, and all the masses do not change between O and O prime. All right, so you don't have to, there is no conversion of the masses m. I think a nice way to think about the fact that mass is invariant is this. Let's say that this velocity right here is the velocity of an electron, right? If that's an electron, then this right here is also the velocity of an electron. And changing observers shouldn't change the fact that we're watching an electron. So why don't we just depend on the fact that all electrons, regardless of who observes them, they have a fundamental quantity called their rest mass that everybody sees. It sort of belongs to their identity, just like their electric charge. So O and O prime won't see different amounts of electric charge, is the idea. They won't see different amounts of mass.